Welcome to this lecture on ordinary differential equations. Today, we are going to explore one of the most beautiful and powerful ideas in all of mathematics and physics, known as the principle of superposition. If you have ever wondered how complex systems can be broken down into simple, understandable parts, this is the secret. By the end of this video, you will not only know how to use this principle, but you will deeply understand why it works. Let us dive right in. To understand this concept, imagine you're standing by a perfectly calm pond and you toss a small stone into the water. You see a neat, circular pattern of ripples spreading outward. Now, imagine you toss two stones into the water at the same time, but a few feet apart. Each stone creates its own set of ripples. When these two sets of ripples meet, they do not destroy each other or create chaotic garbage. Instead, the water simply adds the heights of the two ripples together at every single point where they cross. If two peaks meet, you get a higher peak, and if a peak meets a valley, they cancel out to leave flat water. This predictable adding together of separate events is exactly what mathematicians called the principle of superposition. Now that we have the pond analogy in mind, let us look at this visually. On your screen, you see three separate graphs. The top graph shows a simple blue wave, representing one basic behavior of a system. The middle graph shows a different red wave, representing another basic behavior. The magic happens in the bottom graph. This purple wave looks much more complicated, but it is built entirely from the simple addition of the first two waves, point by point. Wherever the top two waves are high, the bottom wave is even higher. This diagram visually demonstrates how two entirely different solutions can be added together to form a new valid state. This visual idea of adding waves brings us to the formal mathematics. In the study of ordinary differential equations, the principle of superposition applies specifically to linear homogeneous equations. But what do those words mean? A linear equation is one where the unknown function and its derivatives only appear to the first power. You will not see them squared or multiplying each other. A homogeneous equation means that the entire equation is set equal to 0. Physically, this means there are no outside forces acting on the system. It is just evolving on its own. If your equation meets these two conditions, you unlock a massive shortcut for finding its solutions. So, we know the conditions. Now let us look at the actual rule. The principle states that if you have two valid solutions to a linear homogeneous equation, let us call them y1 and y2, then any linear combination of these solutions is also a valid solution. A linear combination simply means multiplying each solution by some constant number, c1 and c2, and then adding them together. This gives us our formula, y equals c1 times y1 plus c2 times y2. Conceptually, this means if you know a few basic ways a system can behave, any mixture of those behaviors is also a completely valid way for the system to behave. Increasing the constants simply amplifies that specific behavior in the final mix. Before we prove this works for everything, let us see this with a concrete example. Consider the second-order differential equation y double prime minus 4y equals 0. We are given two known solutions, e to the power of 2x and e to the power of negative 2x. We want to test if a specific linear combination, y equals 3 times e to the 2x plus 5 times e to the negative 2x, is also a valid solution. To verify this, we need to plug it into our equation. First, we calculate the first derivative using the chain rule, bringing down the constants from the exponents. Then, we differentiate one more time to find the second derivative, which represents the concavity of our function. Continuing with our example, we are now ready to substitute our expressions back into the original differential equation. The equation asks us to take the second derivative and subtract 4 times the original function. We carefully place our calculated expressions into this structure and set it equal to 0. Next, we expand the terms by distributing the negative 4 into the parentheses. When we look at the resulting string of exponential terms, we see that the positive and negative versions of each term cancel each other out completely. This leaves us with 0 equals 0, a universally true statement. Physically, this confirms that scaling and adding our original exponential solutions creates a new state that perfectly obeys the rules of the system. Let us look at another common example, this time with trigonometric functions. The equation y double prime plus 9y equals 0 describes a simple harmonic oscillator, like a mass bouncing on a spring. We are given two fundamental solutions, cosine of 3x and sine of 3x. We want to verify that the linear combination 4 cosine 3x minus 2 sine 3x is also a valid solution. Just like before, our strategy relies on direct substitution. We calculate the first derivative, remembering our trigonometric rules and the chain rule, which gives us the velocity of the mass. Then we differentiate again to find the second derivative, representing the acceleration of the mass on the spring. Now we substitute our combined function and its second derivative into the original oscillator equation. We add the second derivative to 9 times the original function, setting the whole thing equal to 0. To simplify, we multiply the terms inside the second set of brackets by 9. Grouping the cosine terms together and the sine terms together, we immediately notice that we have exact opposites. The negative 36 cosine cancels the positive 36 cosine, and the sine terms cancel as well. Once again, we are left with 0 equals 0. This physically means that a mass on a spring can have a motion that is a complex mixture of a cosine wave and a sine wave, and still perfectly obey the fundamental laws of physics. Now that we have successfully used this formula in two different examples, let us understand exactly why it works by proving it mathematically. We will prove this principle for a standard second-order linear homogeneous differential equation. We start by writing down the general form, using unknown functions p of x and q of x for the coefficients to keep our proof completely general. To begin, we must assume that we already have two valid solutions, y1 and y2. Because they are valid solutions, plugging either of them into our template equation must result in exactly 0. This gives us two foundational equations that we know are absolutely true, and we will use these facts later in our derivation. Continuing with our proof, we want to test if a linear combination of these two solutions is also a valid solution. We create a new function, y, by multiplying our first solution by a constant c1, multiplying our second solution by a constant c2, and adding them together. To plug this new combined function into the differential equation, we first need to find its derivatives. Because the derivative of a sum is the sum of the derivatives and constants simply pull out to the front, taking the derivatives is straightforward. We apply the derivative operator to each piece individually to get the first derivative and then repeat the exact same process to find the second derivative. We now have all the pieces needed for substitution. Now comes the crucial step of substituting our combined function and its derivatives back into the original differential equation. We replace y double prime, y prime, and y with the expressions we just derived. This creates a rather long and intimidating equation. However, our goal is simply to reorganize this long expression to see if it equals 0. To simplify, we rearrange the terms by grouping them based on the constants c1 and c2. We gather all the terms multiplied by c1 into one set of parentheses and all the terms multiplied by c2 into another set. This algebraic reorganization reveals a beautiful pattern. The expressions inside the parentheses should look very familiar to what we established at the very beginning of our proof. In this final step of the proof, if you look closely at the expressions inside the parentheses, you will see they are exactly the original equations for y1 and y2. Earlier, we established that because y1 and y2 are valid solutions, those exact expressions are equal to 0. Therefore, we can replace the entire contents of both sets of parentheses with the number 0. By substituting 0, the constants C1 and C2 are multiplied by 0, meaning the entire left side of the equation collapses. We are left with 0 equals 0. Because we arrived at a universally true statement, the proof is complete. This mathematical proof guarantees that the combined function is indeed a valid solution, confirming the principle of superposition for all linear homogeneous equations. So we have proven that this principle holds mathematically. But why is it so important? The principle of superposition extends far beyond just passing a math class. In structural engineering, when designing a bridge, engineers must calculate the stress caused by the weight of the bridge itself and the stress caused by the wind. Because the equations governing small deflections are linear, they can simply add these stresses together to find the total stress on the bridge. Similarly, in electrical engineering, the current flowing through a complex circuit with multiple batteries can be found by calculating the current from each battery individually and then adding them up. Without superposition, modern engineering would be nearly impossible, as we would have to solve every complex problem from scratch. Let us summarize the key takeaways from this topic. The principle of superposition is a powerful rule specifically for linear homogeneous differential equations. It guarantees that if you have a set of individual solutions, you can multiply them by any constants and add them together to form a new perfectly valid solution. This property completely transforms how we solve differential equations, allowing us to construct the complete general solution from a few basic building blocks. It is the mathematical equivalent of knowing that if you understand how individual instruments sound, you can understand how an entire orchestra will sound when they play together. You have now mastered both the application and the proof of this fundamental concept.